lecture number 4, and we're talking today about the appropriate microcontroller use. So when is a microcontroller the appropriate device to be using? We're going to be looking at that in a number of issues. In particular, is it better to use maybe something else, some alternatives? So here are some alternatives, and these are the things that you all are looking at as you prepare for this presentation that you'll be giving. We will have each of you look deeply at one of these, but altogether we want to see when is it appropriate to use a microcontroller. So let's take a brief run at these various other technologies, processing technologies. So first we have the ASIC. The ASIC is an application-specific integrated circuit. So the fact is it's specific. It's not general purpose. And because of that, we have to be careful because you may or may not be able to even use one because it may not satisfy it might not be able to do what you want it to do. So the fact is that these are optimized for certain problems. So they may be defined to work, for example, within an automobile and do certain functions within the automobile. Okay, so if you want to go and use it for something else, it may not work, and so that is an issue. And we have two varieties of ASIC. You have the fully custom, where all layers of the integrated circuit are optimized for the application. And then we have the semi-custom, where the bottom layers are optimized. So in this case, this is fully optimized for a specific problem. So there's no flexibility. You can't change it. You can't use it for something else other than what it was intended for, pretty much. Whereas the semi-custom basically has the bottom layers that are optimized, and the top layers are available to modify. So we have a little bit of flexibility with this. But the nice thing about these is, in general, they're very fast for what they do. They're as fast as possible, pretty much. Low power, all that kind of stuff, but not very flexible. Application specific. So number of manufacturers make these, but again, they have their place. They serve a very nice role. Next, we have a CPLD, complex programmable logic device. So programmable means obviously you can change it. So it's in between a PAL and an FPGA. So PAL is smaller, FPGA is bigger, but they actually do things a little different. So the CPLD has as its basic block within it what's called a macro cell, which basically means within the chip itself there's what they call a sea of gates, a bunch of gates, and you can interconnect the gates to perform certain functions. So the chip itself may contain non-volatile memory. Volatile means that when you turn the power off, it goes away. The memory gets erased or modified. Whereas non-volatile means if you turn the power off and you turn it back on, it retains what was in memory before. So that can be very helpful for a lot of applications. Some cases it doesn't matter. Some cases it does. Fast and flexible. The processor is fast and flexible. That is, you can set it up to do lots of different kinds of functions. Not everything, but you can do a lot of good stuff. But it's complex, and the programming can be fairly complex as well. Next, we have an FPGA, which is an important one, Field Programmable Gate Array, which basically, internally, there's a large interconnection matrix of connecting different devices together. There are logic gates. There is random access memory. Generally, that is volatile memory on the device. The FPGA may actually have A to D and D to A converter capability, so that is something that may be resident on board the FPGA. In general, it's programmed by a computer. VHDL is a very common way to program these things, and so that's what the FPGA does. So it's a chip, but internally you have different things going on that you can work with. So that's the FPGA. Next, we come to the digital signal processor, DSP. So the fact that it has the word signal in there means that it's designed to work with signals and to process them. So there's generally some serious number crunching capability in here. You may have a number of parallel computational pipelines. It may be the whole system is designed around inputs and outputs, digital and analog inputs and outputs, and so it's designed for that. So it is in some ways it is very effective working with those things. In addition, the inputs may include things like quadrature encoders, so in other words, and this is something you're going to learn a bit about, is something called a quadrature encoder. Quadrature encoder is often used for things that have rotary motion, and it's a way of encoding position information using digital, using basically 2 bits or 2 signals, digital signals. And so the quadrature encoder then needs to be decoded in order to use that information. So this includes the decoders. In a lab, you will also be doing some decoding of quadrature encoders, so it's helpful to know what that's all about. Okay, so when you do that, you'll appreciate the fact that some DSPs have these kinds of capabilities built right in. That's really handy. Pulse width modulation, we're going to learn about that. And so again, some of these DSPs have pulse width modulation as a feature of that system. They can also do serial communications, SPI, or I2C communication. So FPGA, the DSPs have some very nice capabilities. Programmable logic controller. These are designed for industrial applications. Now, the first time I went to work in industry, I went and worked for a company that manufactured stuff, and they controlled things digitally, but they did it old school, before computers were common. So, yeah, I'm that old. And so in those days, they used to use something called relays. And we still have relays today. Relay is basically a switch, electronically controlled switch. And so basically everything was controlled, just like a microprocessor, only it was controlled by discrete switches called relays. And so if you have all of these things happening, so we just kind of take for granted that the computer knows what to do with the bits. Well, when you do relays, you actually have to hardwire in pretty much every bit. Okay, it's pretty complicated. And so when the relay makes a contact, you can hear a little click. And so in this manufacturing plant, they had rooms full of relays, and you would just hear them clickety clackety clickety clackety clickety, because there's all this stuff going on in the manufacturing, and it's all being controlled by relays. That was its brain in a sense, and it was quite complicated, but lots of relays. So basically, the programmable logic controller basically took over the function of many relays using a microprocessor. And so what was once a room full of relays now fits in a nice little package like this, where you have not only the capability of doing relays and such, but you can also hook up USB ports, and you can do other things associated with this. So a PLC, programmable logic controller, is a system that is primarily designed around industrial applications. It's ruggedized. It can handle high power stuff. It's very expandable via modules. By way of modules, you can add different modules to do different things. You can get a PID module that does automatic feedback controls, and so all kinds of things. So very broad range of capabilities. It can do centralized or decentralized control. So centralized control means everything is controlled from one central box. Decentralized control means I can have a box here, box here, box here. This box controls this stuff over here. This box controls this stuff over here. This box controls this stuff over here. And so you have a number of boxes, and they can interconnect. And so that's decentralized control. So these things are often programmed graphically. And again, they do it using often something called relay ladder logic. So the ladder logic is a carryover from the old relay system. So anyway, that's the PLC. It's a different way of thinking about controls, but it's a very important way that is used in industry. Many industries use these. Another alternative to the microcontroller is the microprocessor, or the computer. So in general, the microprocessor can handle math. So in fact, many microprocessors have built-in math coprocessors. So it knows how to do a divide very fast. It knows how to do transcendental functions, cosine, sine, arc cosine, and so forth. So a lot of those math computational things it knows, and it has the fast capability of doing those kinds of things. It's often designed with certain peripherals in mind. So all computers pretty much are designed to handle a keyboard, some other input device like a mouse. They're designed to have video capabilities. Okay, so microprocessors designed with certain peripherals in mind. However, they're not generally designed to directly interface with either analog or digital inputs. The only possible exception is with audio, if your computer has an audio card. Okay, so now it used to be in the early days that some computers like this had all that stuff built in, like audio card. Some of them didn't, and so now pretty much all computers have audio, but in the early days they didn't. In general, a microprocessor is connected with a significant amount of memory. We can talk about gigs and gigs of memory. That's a lot. The microcontroller on the Arduino has 32K of memory. Not very much memory. 32 kilobytes versus my laptop here, which has 8 gigabytes. Okay, so 8 gigabytes is a lot more than 32 kilobytes. So significant amount of memory. In general, these guys run an OS, some kind of an operating system. So this has the Mac OS. This is a Raspberry Pi, which is a single board microprocessor or microcomputer. And this runs Linux. Okay, the Arduino also has a couple of different variations that will run Linux as well. The Arduino Use, for example, will run Linux. The Use actually has a single board computer type situation, and on the same board it has the functional equivalent of an Arduino Uno on the same board. So it does both, and they're already interconnected. So in a sense, it has two processors. One is the microcontroller processor, and the other is the microprocessor. But the microprocessor in general is different. Just the fact that it's running on an OS as opposed to just running its own little code that's a very different thing. So they may be single board like the Raspberry Pi or some of the others. So these can serve as an alternative to a microcontroller if you need what they can do, for example, like math, or being able to handle, if you want to display like a monitor, if you want to be able to connect the keyboard up and all those kinds of things, audio, then this may be the way to go. Alternatives to a microcontroller. Well, another alternative is a microcontroller, and there are a whole slew of microcontrollers. So the Arduino itself has 20 different varieties. Here are some of those varieties. The LilyPad, this is the Uno, here's the Arduino Ethernet, here's the Leonardo, here's the Mega, here's another variation of the Mega, and so forth. 20 different varieties of the Arduino. There's also the Make controller, there's the Pickaxe, there's Basic Stamp, there's a whole bunch of different types of microcontrollers. And so it's important to understand with all this wide variety of options, how do you decide what you're going to do? So we're now going to talk a little bit about the selection of a microcontroller unit. Okay, so in terms of the selection, we ask the question, how do you choose the microcontroller unit? Well, I'm going to describe for you a little process by which you can go through for a given problem to look at how to answer this question, how to choose a microcontroller unit. So the first thing you need to do in choosing the microcontroller unit is to define the system requirements. What are the basic system requirements that the system must do? Okay, do you need to have it connected to analog or digital? Do you need to have timing functions? Do you need to have, what do you need? What do you need? That's the question. So system requirements are a very important part of picking the microcontroller unit. You need to have a clear idea. And in picking or in determining what the system requirements are, you need to think of a couple of different things. First of all, you have what are called hard requirements and soft requirements. Hard requirements are requirements that are absolutely necessary. If you do not have these requirements met, then your system will not function, will not accomplish the function that you need for it. For example, if you need analog in and your microcontroller does not have analog in, you will not be able to satisfy the requirements for that project. So you need to have what are called hard requirements. These are all the things you absolutely need to have. Then you have what are called soft requirements. These are things that would be nice to have. Not absolutely essential, but it would be nice. And again, there can be a priority among these different requirements, but it's very important to define what those requirements are. For a specific problem, what are those requirements? So that's the first thing, defining those. And we're going to talk in a little bit about various types of system requirements that a system might have. So the second thing we have is we need to choose the processor technology. So we've seen that there are a number of different options available. Do we want a microprocessor versus a microcontroller? Do we want a DSP? So we need to choose the correct processor technology. What is the technology that we need? So based on the system requirements, what technology are we going to use? Do we need TTL? Do we need CMOS? So those are some of the kinds of things we look at. Then we're going to list all good candidates. Okay, what are all the good candidates among what's available, or at least what we know about? Okay, they're coming out with stuff all the time. There's stuff that has been on the market for a long time, and maybe we're not even familiar with it. Okay, so obviously here you can't put something down if you're not familiar with it. So obviously this is only the candidates that we're familiar with, but it's important to list them and their pros and cons and capabilities, whether or not they can adequately solve the problem. So all of these good candidates need to basically be able to solve the problem. They need to be able to meet the hard system requirements. So then they absolutely have to meet the hard system requirements. If they don't do that, they don't make it on this list. Okay. So now among the soft requirements, that's the kind of thing that we do in the next step. We need to finalize the selection by looking at the soft requirements. Okay, so in other words, for example, I'd like it small, or I would like it to be low power. I would like it to use 3.3 volts instead of 5 volt. Okay, so there are a number of different things that could be those soft requirements, and so you need to look those in order to finalize the selection. And you might come down, and there are two, and it's they're about equal with each other, and that's okay. And you just need to pick one. So it may be also that one of your soft requirements is that you use an Arduino Uno. That could be a soft requirement. Okay, it's not absolutely necessary, but it's something that you really want to have. And if you come down to two, and you come down to two options, and one of them is the Arduino Uno, and that meets one of the soft constraints. Okay, so that may be an obvious choice based on your constraints. Okay, so selection of the microcontroller unit involves looking at all of these four things in order to make a good choice. So that's important. Now, System requirements. There are lots of things that could appear as system requirements. This is just a list of about, well, 19 different things. But all of these are very important. And a person could spend their life trying to find out everything about all of these things for a particular problem. And it may be that some of these really are not as important as others. There's probably a priority among all these things. So these are important. All of these are important. And there are other things that are important too. Let me just talk a little bit briefly about each of these kinds of. So you've seen part of this list when we looked at for your project that you're doing, your presentation. You've seen part of this list. So computational power basically refers to the ability to do number crunching. So if your system has a math coprocessor, it's probably going to be a lot more effective at computational power. If your system has 32 bits versus 8 bits, it's going to generally have more computational power. For the same clock speed, it can do things a lot more either efficiently, effectively, or So computational power is important for a lot of systems. For some, not so much, but that can be a requirement. And these are not listed in any particular order of importance. The importance lies in the problem that you're trying to solve. Okay, the problem that you're trying to solve will determine the importance of these kinds of things. Ease of programming. So, for example, the Arduino has the nice IDE, which it makes it very easy to program. It's designed for hobbyists. It's not designed for technical people. So it's going to be a lot easier to work with than some of the others that are out there. Some of them are really a pain to work with. Okay, even some of the Arduinos are a pain to work with because they don't connect directly with the IDE. So that can be a problem. So ease of programming is definitely an important thing. Okay, so if they have some very odd proprietary programming thing that's tricky to learn, that's something to take into account. If they use standard software type tools like C and C++ is important. Another thing that's not mentioned here that also goes with programming is the ability to debug. That can be a huge thing because you may have developed all this code, lines and lines and lines of code, and now you have to go through and debug it and check to see if it's got errors. What kind of tools are available for debugging? Okay, some of them actually have hardware simulators that can do the debugging and emulators and things like that, so you can actually analyze your process very effectively using another computer. And so debugging tools can be a huge matter because if you have lots and lots of code, it may be very difficult to find. Your system is doing something weird, and you want to figure out why, and it can be very complicated to find out what's going on. And so if you have some nice debugging capability, that can be a huge benefit in your development of your system. Speed of operation. So speed of operation here sometimes it's referred to as throughput. So remember, your system has a number of things going on all at the same time. Okay, so you've got inputs, you've got outputs. Okay, and so for example, we talked a little bit about latency. Okay, latency. In other words, is there a delay in the system? Okay, so certain processors have more of a delay on certain things than others. Okay, so if, for example, you want to use your microcontroller system to do some analog processing, let's say your guitar signal. You got a guitar, and you want to be able to do some signal processing with your guitar, and so when you do analog to digital conversion in order to put the analog guitar signal into your computer, it takes a little time to do that conversion. Then it's going to take some time to do the processing, okay, which may involve some number crunching, may involve some other things, logic functions or whatever. And then it's going to take whatever signal it needs to and output that through some means. And so the whole process from the time it starts, from the time it grabs a value to the time it puts out a value, there may be some delay, and that's often referred to as latency. And so the speed of operation can be related to the latency of the system. How much delay is there in processing information? Does it happen lickety-split so that when you're playing you don't hear a delay between the time for example, you pluck the string and the time the sound comes out? Or is there a delay? And is it noticeable? And is it annoying? And so the speed of operation can be something. Interrupts. Can your system handle interrupts? Does it have the capability of having a signal that you apply? When you apply that, it stops whatever the system is doing and goes and does some little function and then returns to whatever it was doing before. Does it have that capability? Some systems don't, and so interrupts can be an important thing. Reconfiguration. How easy is it to reconfigure the system? You're using it for one application, you want to use it for another application. How easy is it to reconfigure from one to the other? Power or heat. These two often go together. What are the power requirements for this device? Is this one like really power hungry? So this kind of thing can be a big deal if you want to make, for example, an autonomous robot, something that basically carries its own power supply with it. You don't plug it in, it has to carry its own power supply, which is often like a battery or maybe photovoltaic cells or something. But it carries its own power supply with it, and if it's really power hungry, it's going to go through that power very quickly, and so that, you don't want something very power hungry. Okay. And so that's power side is important if you're using batteries, for example. You don't want to use up your battery too quickly. On the other side, if it's power hungry, it might also make the system very hot. Okay, so in which case you may need special cooling, or you have to do something to keep it from frying itself or whatever, or heating up the entire system. So those are some considerations that can be deal breakers in some cases. Okay, so depending on the system requirements. Okay, so power or heat. What about the ability to interface or the compatibility? In other words, how easy is it to connect up analog signals? How easy is it to connect up digital signals? How easy is it to for example, can it handle TTL and CMOS, or do you have to do some kind of circuitry to convert from one to the other in order to use it? So that's the issue of compatibility. Is it CMOS compatible? Is it TTL compatible? Okay, so those compatibility issues are important. Maybe there are certain devices that have a specific plug, and you can plug it right in, or do you have to come up with your own plug to plug it in? How easy is it to connect what you have, like for example, sensors and actuators, directly to your microcontroller? That's the issue of interfacing or compatibility. Overall cost of the system. So you have two different systems. One maybe is easier to interface, but it's a more expensive system, whereas this one is more difficult to interface, but it's a cheaper system. So you have a number of things that can be trade-offs, but the overall cost of the system can be a huge deal. And so, some, even among the Arduinos, you have some that are fairly cheap, $10, and then you have some that are really expensive, like $80, okay, like for the Arduino Use. Versatility. How versatile is it? That may not be important, but it may be important. So the idea of versatility is, how can I use the same thing for lots of different things, for lots of different applications? So it's kind of related to reconfiguration, but reconfiguration generally involves, for example, 2 or maybe 3 different functions that the thing does, and I want to be able to switch back and forth between them. Okay. Whereas versatility means, could I use this same device to do a dozen different things? Maybe not, switching them out really quickly, but can I use the same thing, or do I have to buy one device for this, one device to do that, one device to do, or can I just buy one device that is able to do all these different things? Okay, so that's the idea of versatility. Whereas reconfiguration is how easy is it, can I switch between two fixed applications quickly? So a little bit different. Communication. Can I communicate with other devices? So we've talked a little bit about communication, serial communication, but there are lots of different kinds of communication issues. So, for example, in modern automobiles, the number of microcontrollers being used in automobiles is increasing. So it used to be that they maybe had one microcontroller on board of the whole car. Now, some of the cars, especially some of the high-end cars, can have 5 or 6 microcontrollers. One that controls, for example, the temperature of the interior of the car. Okay, and so it has sensors and things that will hook up to the air conditioner, the heater, and the fans, and basically do what is needed to control the temperature within the interior of the car. That has nothing to do with the car rolling down the road. It has to do with the comfort. Okay, and so you can have a number of things. There are more and more microprocessors within the car, and so those microprocessors may need to talk to one another. Okay, or you may have what are called smart sensors, a sensor that can do some interpreting of the results that it's sensing and send it to the microcontroller. So can it communicate with that? So how easy is it to communicate with other devices? And there are standard communication protocols. For example, the SPI, the I2C. On an automobile, they use something called the CAN, C-A-N, Controller Area Network. Okay, so how easy is it to communicate with other devices? Okay, so that can be a huge thing. Safety. How safe is the device? Okay, again, totally different thing, but obviously important. If safety is a factor, then this is important. Safety can be it's a big thing. It can be very complicated. It can relate to the fact that if so for example, if you think of a car, you have this microcontroller in there, and if something rattles around and shorts two connections on the microcontroller, you've got some dust, or let's say a staple just kind of gets loose in the car, and you hit a bump and the staple jumps up or whatever, and it makes a contact with two. What's that gonna do? Is that gonna be a problem? It's gonna touch your circuit board. Is that gonna create a problem somehow? So that's an issue. Safety can come up in a number of different ways. Is your system robust? Okay, that is the heat going to mess things up so that down the road the heat and expansion cycle from morning to evening to night to, is that constantly changing in heat can cause things to expand and contract? Is that going to cause some kind of a safety hazard down the line? So sometimes safety can be very complicated to analyze for a system, but obviously if there are safety issues, you definitely want to know about them, and you definitely want to avoid whatever would cause them. And sometimes it can be the microcontroller. Okay, so safety is an important thing. Upgradability. Can I upgrade the software? How easy is it to upgrade the software? How easy is it to swap out the hardware to a new model that has new features, better features, or whatever? Upgradability can be huge. Memory. Is memory important? Do you need to keep track of a lot? Sometimes you do. And memory can be a big issue because you may need a lot of memory. You may need to keep track of a lot of stuff. What about timer counter functions? Do I need those? Okay. Does the unit that we're looking at have that capability? Handling media, is that an issue? Okay, so more and more cars are now wanting to have things that can handle media. Okay, can the device you're using handle media? What about the overall time required to assemble the system? Is it so complicated that you have to hook this up, You have to solder a big circuit together before you can get the thing working. That can be a huge issue. Overall time required to assemble the system. That can be an important factor in the choice. EMI or EMC, electromagnetic interference, electromagnetic compatibility. So how good is the device at rejecting interference? So for example, let's say in the early days of the use of microprocessors in an automobile, there was one of the applications was a cruise control in an automobile. This is actually by the Cadillac. They were one of the first ones to implement a cruise control in an automobile. And so they were taking it out for a test drive, the cruise system with the cruise control, and they went underneath a power line. Or this is how the story goes. I'm not sure if the story that I heard is absolutely correct. But anyway, they went underneath the power line, and the electromagnetic interference from that power line did something to the microprocessor that made the throttle stick down, and so it just accelerated, and so obviously that's a safety issue. But it boiled down to the fact that there was everything functioned properly, but it did not have electromagnetic interference capability. It couldn't handle that electromagnetic interference. Couldn't handle it. And so that was a problem. Obviously a problem. They needed to do something to fix that. Okay, they needed to have a system that could handle that interference. On the other side, electromagnetic compatibility is the question: is my device putting out electromagnetic radiation, and is my device creating problems for other devices? Okay, so that's an important thing. Now, a lot of the devices are screened for that and checked to see if they meet certain compatibility requirements. But again, that's important. Some will put out more than others. And so, is the system that you're working with, is it going to be okay with that? So, important thing to consider. Size. Is it okay? I mean, do I want a small thing? Do I want a bigger thing? Am I okay with a bigger? Generally, we want small because we want to be able to fit it in a small space. But am I okay with a bigger thing? So size can be a big thing, can be a deal breaker. Availability. You may have got what looks like the perfect setup. This particular device is exactly what we need, but we can't get them. They don't make them anymore, or they've discontinued it, or they're on back order, and we can't. They're going to be back on back order for 3 months, okay? Because they're not going to make any more for 3 months, or whatever. I mean, availability. So everything else, all of this other stuff could be great, but they're not available, okay? And so that's a requirement. It has to be available, okay? So these are a number of so many issues, okay? It's like when you want to go buy a new car, for example. What do you look at? How do you decide? There's so many things to look at. You can look at the paint job, you can look at the upholstery, you can look at the engine, you can, and even within the engine, you can look at various components within the engine, and there's so much stuff to look at. How do you make a decision? Well, at some point, you just have to make a decision. But there are many things to consider, and the more things that you consider, the more likely you're going to be end up with a satisfactory end result. So this is the issue of appropriate microcontroller use. Under what conditions? Well, these are some issues to consider in evaluating whether a particular microcontroller is appropriate. What needs to be seen now is specific applications, and you will have opportunity to look at some applications in your projects. So this is lecture number 4. Thanks for watching.